Regarding myself, I've been with the VW Group already for around 3 years in the topic of autonomous driving and in different positions. I started my research from the year 2018. What I would like to present to you is the latest research, and also to mark down our legal disclaimer that all views are my own, not my employee, and my employer cannot be held accountable anyway for or liable for the usage of this information, and it's just purely for information purposes. From there on, I just would like to give you a small overview about the type of AD development that we do research, which we actually call ourselves Group Innovation, and also about the view of certain examples on the particular projects that we do. And then let's get to the core, which is ensuring that data quality, data reliability, and determining quality metrics and particular challenges that we have in AI can be, in a way, through a method ensured. So this is just the method. I'm not here posing any type of assurance in an absolute way. These are theses. They must still be validated in the vehicles. So far, there's a particular further needs for research. So this is just a method I like to point out. About us, we actually, I like to kid about that we're a big bank with a very, very small technology department. I sit down in a group in the central mother AG, which we have just several type of direct companies, mostly which is known to use the automotive division. We've got passenger cars, we've got commercial vehicles, Audi, Porsche, Bentley, Skoda, Seat, and as well as then Cupra and other type of, let's say, direct companies that just been recently been started, like Carriot or Cyctic, for example. And as well, we've got a big lorry type of products, but mostly actually we earn through financial services. We're one of the biggest groups in regards to automobile manufacturers, as well as components. Yeah, so we actually have OEMs as customers, and you might have heard of our cooperation then with Ford, for example. As well, yeah, so we are in around 27 countries. In the area of research and development, we're around 42,000 people. And I like to start then further on with the topic of today. I always like to show this piece of information because there's a lot of talk in the media about what is truly the difference between assisted drive, highly automated drive, and when do we really jump into the autonomous world. So everything that you see here, from Tesla's autopilot to what will be then the super cruise control from GM, etc., it's all level 2++. So in this level 1 and 2, so 1 would be like your ABS, ESP, 2 would be as the other 2 functions mentioned. You do not have redundant systems, and the driver is always responsible for ensuring then that traffic control is maintained, the particular trajectory is maintained, and the driver is always the safety case in case there's any issues within the system. When we really jump on level 3, in which we're really talking about highly automated drive, this happens only in certain environment conditions. For example, the traffic jam pilot from our competitor in the southern part of Germany, which is already brought into the market. This only works on particular speeds and on particular environmental conditions. So here was talking about level 3. And even though the vehicle is designed to take on if there's any errors, and it is redundant, for example, the braking system is redundant, the energy system is redundant, the driver is still being used as a fallback system. So for the talk of today, I'm really talking about autonomous levels. So the level 4, level 5, in which here we're talking already that the vehicle is at any moment responsible to ensure that the driving maneuver has been finished, to ensure the safety of all traffic participants, be it pedestrians, be it people on a bike, be it people on a moped, it doesn't matter. Here we've got a redundancy of all actuation and then of all perception. At the same time, we could have a system with a mechanical backup. For example, you might have heard about our new concept, the Auto.AI, that the driver can choose to be in a completely then autonomous pod modus, or decide to do the actuation himself, steering, braking, keeping throttle. Or what will be then other projects that we have to be working as an autonomous shuttle. At the same time, this at level 4 still works in certain environmental situations and at the same time on certain scenarios. So here we're talking already about highway pilot at level 4, a robot taxi shuttle, and we got a vision here for the future. You might have seen Cedric. So level 1, level 2, you see our traffic jam pilot from level 3, as well as the highway pilot. We've shown this at other events, but the one I want to connect with you today and talk about in regards to data and AI is in the level 4 and the robot taxi, which can be hop to hop, door to door, and is what we still consider to be the future of mobility. But first on, I'd like to use this slide from the Technical University Darmstadt. We also do a lot of cooperation. To give an example about the system architecture for level 3, level 4 architecture. So the number one thing is we've got the entire redundancy of the system, as already mentioned, including longitudinal and lateral conditions for control, as well as decision-making and safety security. But the main challenge is actually taking on the driver tasks. So that is knowing what to do, understanding traffic signs, understanding traffic rules, which is the main challenge for any robot. In this case, that is the new thing that we must ensure, as well as know how to drive. So what is the best driver? Is that a very conservative one? Is it a sporty one? Is it the one with the most hours on the street? That is here what we mean about skill-based behavior. And then from there, learning to navigate, select the best route, best time schedule, guidance conduction, so for the particular direction that the vehicle should take, as well as ensuring it's always stabilized, never coming up to the dynamic limit, as well as understand the road, the environments, which across Europe, we don't even have a standard. A highway looks completely different in Belgium, for example, compared to Germany, as well as the traffic situation and the road surface. So when we're talking about what we're doing right now, usually the new thing is to cover the yellow area. And where we have a lot of experience is on the green area. Another particular of autonomous driving is that we work doing scenario-based development. So what actually is this? So a scenario is nothing else but the particular activity and sequence that a driver would do, for example, while taking a car on the road. In this case, we've got an action, we indicate we want to change the lane, then we really do a lane change when we see that there's a particular free spot, as well as then the action then to follow along and continue then in the middle of the road. And then for that, we have a particular need. So what we call a use case. So for functional range, for desired behavior, all the system boundaries. And in autonomous vehicles, the system of systems is not just the vehicle, but also its connection to 5G network, for example, 4G network, high definition maps, to GPS, or other vehicles or infrastructure for V2X. In regards to the SEAM, is what we're doing here is the representation on exactly what the vehicle should do. And the scenario here is all the action, all events, including what we want the vehicle to do here. So keep itself safe on the lane and only change the lane, for example, if there is a free spot. So now about safe AI. So according to the market, so artificial intelligence in 2020 generated over 22 billion US dollars. So it's a one of the most important innovation topics to take care of. So its critical use, it's mostly been used for projective threat detection, which is what we want to continue on in the automotive industry. So currently we use it for perception to recognize if it's a car or if it's a co-cab, for example. So artificial intelligence must detect these dangerous situations as well as then continue to learn and include in these algorithms a particular safety and security case to ensure that the car, the passengers and everyone around is safe. So the algorithm so far plays a major role. But as mostly what is most important thing is actually the incoming data. So what is the vehicle, what is the road sign, and what is the potential hazard, and which are everything that needs to be taken into consideration so that the vehicle can behave accordingly. So I took again another very interesting slide from the TU Darmstadt, in which usually we ourselves in the automotive industry, since the ISO 262 got published in 2011, got a lot of experience on understanding what the critical scenarios are, ensuring through hazard and risk analysis what is really then the functional safety that should be taken care of. But it didn't take care of any kind of functional insufficiencies, which is where automation accidents could happen. So is trying to find a needle in a haystack. So in order to get this safety of intended function gives us so far this past tender a way, a format then to bring on about how could we maybe ensure that the vehicle is safe across the entire system. So what we've been doing, a lot of monitoring across the entire architecture with different type of plausibilities, as well as the typical safety critical management based on the worst case scenario. And what's coming on new for us is the continuous deployment. So how can the system recognize new situations and act appropriately? So when we go on into machine learning in chassis systems and physical dynamics, we must first make the difference between what functional learning is and what deep learning is. So one for road classification, for interpretation of what's going on across the car and within the vehicle, and in functional learning to ensure that we prevent accidents and improve the controller quality and adapt the vehicle controller as necessary. And at the same time, then maybe individualize the vehicle, making it either sporty in the drive or much more comfortable in the drive for the passengers. So just to give you a way, this already might be very common then for you, but just going again really, really fast through the top of technical architecture. We got again our perception technology, as well as then our particular video technology, radar and LiDAR technology. But the main thing to concentrate here is on how we could prevent any type then of errors within the AI. So in our sense, act, plan, typical architecture, we first started up with bringing neural network for object detection and scene interpretation, as well as having a neural network for decision making, path planning, as well as having a neural network for controller. This is a typical architecture. But the important thing is then to know, well, if we fuse all of this and use this to create a parallel divergent neural network and take on the advantages that on a level 4 we got two redundant system, we can use the input from two different channels in order to create then two different type then of AI input, as well as monitoring for vehicle control. So one of the things that we've got to take into consideration is, well, when can we collect this data? And it's already mentioned, we're extremely dependent on the environment, extremely dependent on certain conditions, and the biggest challenge of us, dynamicity of the human decisions from other traffic participants, as pedestrians, for example, or in the case here of the highway, of motorcycle driver, which they take on sometimes different traffic rules as a vehicle would do. So let's take on the first example from image segmentation, from which we've got exactly, let's say, the typical type of architecture of everyone else, from our sensor, fusion, main function, and then again the backup, and then the decider and redundant actuation, and then put it up into our deep pilot driving, and then bringing about all this information on a particular convolution neural network. So the important thing about this AI, which a lot of people say, well, we don't know exactly what is happening here. The principle that taken here is to simply simplify it, bring it less layers, but not less convolutions. And in first, we figured out that the layers were not as important as the convolutions. So we did this on 3 different type of environmental conditions. So the sun at midday, the sun around 4 p.m. and when the sun is setting late at night, taking about all this data, make the unit learn, and then make the vehicle decide and actuate. And then we did the same thing by using then another redundant system input, and in which we did again the convolution, did a different deconvolution, and then try then to analyze this data as to make a comparison to create 2 different type of metrics, the reliability metric and an error rate metric. So we use the Cityscapes data set for semantic scene interpretation, extraction of static and dynamic objects, and recognition of dynamic objects in order to enable also the road surface boundaries, in this case here, the posts on the street. So the safe AI method, as already mentioned, is first use one of the channel using a typical algorithm cluster, and then use a secondary channel with secondary diverse inputs, and then here use a particular classificator and cluster to figure out, well, which data might be the most reliable. I got a bit of that. So why to use then CNN above anything else? Well, everybody's using Bayesian methods, but what we figured it out is that they're usually intractable, so it can only be computed approximately. Another way, which is being proposed by Lakshmirian, is, let's say, to use non-Bayesian uncertainty. But usually what's going on is that the neural network is trained with the same training data. So here you got just homogenic redundancy. So our proposal is that we say, well, train it really with using both channels within the vehicle, and then try to understand what's going on. So the KNN first recognizes and chooses then based on the secondary channel. So we first went through one particular ID data and told the classificator, well, this is a road, this is a person, etc., and then brought it about to make a first decision as if the secondary channel is making exactly the same type of recognition. So in that case, then we give it then a declaration flag as confident, that means certain and correct, and call this our accuracy rate, and then we did the contrary. So if something was wrong and it was flagged as wrong, we gave it then a high confidence of certain but incorrect, and then just label this our error rate. So does it help us to find our needle in our stack? I say, well, it might not help you make a hole in one if you're a golf player if you're playing 5 to hole number 7. But if you imagine that particular, let's say, golf hole, just to use again the golf analogy, just imagine bringing that hole and making it at 5-meter diameter. So when you swing the ball, it comes closer to the particular hole, and you might just need one strike more to make a hole in one. So it's a similar principle here that the darker in the classificator and the particular marking label, then the higher we can rely that the particular data being used is accurate, or there is an error rate. So here I pose the thesis that all AI models are as wrong as the data, or some are as useful as its data, to modify the saying of another very famous professor. So how does this improve into the functional learning about the controller? So you see the particular accuracy rates, and what you can see here in blue is the particular trajectory, what the vehicle learned then before, then in blue. It will only react if there's a high level of confidence, to make the decision to transition a particular driving mode. So we use this then for a particular path planner on lateral control, and have it compete with a jaw angle control. That's just a typical thing, and then use then the neural network for that. So as you can see it from here, the particular decision making from the trajectory, from using the typical, let's say, control that we've been using in ADAS level 2++ for over 10 years, versus for the particular neural network base then in green. And the reactions and the decision that's been made in regards then to the keeping the vehicle stable is a considerable difference. So you can see it here, working on making the clustering and giving the decision free on the red line to make the particular lane change maneuver, and keeping the vehicle stable if there's any type of flagged error, which we inputted artificially. And then you can see the blue line here compete with the green line here, the CNN-based redundant path. And you can see the clustering algorithm flagging when a particular sensor perception error was being made, and then stopping the vehicle or deciding to make then a different decision. So just to come up in the summary, we still believe that the CNN, so deep learning, shows a great potential to solve many challenges in the piloted driving architecture. But we still see that the main thing was bringing about the scalability of the data, and also that even though we've ID'd some data, we ID'd twice, there's a really high demand for semi-automatic annotation. So that would be one of the most interesting use cases coming up in the industry, someone that can help us label automatically as much as the data around the road instead of the particular sets that we're using. As well, of course, turning the data and generating it using augmentation and simulation, so scaling up through different roads, different traffic rules. And then again, the next challenge that we will put on and bringing about on these first thesis is, can neural networks meet the ASIL safety requirements? So that is the next point that we're coming up with our research. It's how to bring on the ASIL compliance during the product lifecycle collection, and how to standardize test processes for neural network applications. And here is what actually would be one of the most important things to make a decision within the industry as to, well, is the way that we're testing right now, as we're proposing in this thesis, let's say, gone about to bring the needed safety results to meet the ASIL, yes or no? What else can we do in order to ensure that AI is safe? Well, thank you very much, and I'm taking some questions now.
Thank you, Catherine. A very, very interesting presentation. Thank you very much. And your comment about data modeling was really spot on. Well, we have a direct question from the chat. It was about how can we use AI for ethical decision-making for autonomous vehicles?
I'm not an ethicist. So that is actually only a question that I can answer through my personal opinion. So don't shoot me, please. And then again, I'll say that, first of all, get your ethicists and also get your particular traffic lawyers, as well as then have a particular, let's say, understanding about the rules and talking to the governmental entities, as well as understanding all the traffic rules. So we've learned through the ICE data bank in ISO 262, which is the one that's mainly used for in-year and traffic accidents, as to what has been happening on the road. So how good is the current driver before how good a particular car should be. So taking on from all this data and making, let's say, a panel discussion with bringing the government, bringing the law, bringing, of course, ethicists, I think will be a way to get close.
Brilliant. And one last question from the chat: how to ensure true redundancy, for example, full independence between the processing channels?
In that you really make them separate. So we really have actuations twice, and they're completely independent from each other. That means different energy source, different batteries, different brakes, different, let's say, powertrain control. So they're within the vehicle, and what we have is a decision maker that's also redundant, to make the transition if one channel goes off, then to really swiftly, without the passengers or the drivers checking on about, to be able to make the transition. So they really got to be independent, but have also a reliable source for, let's say, making the transition during the drive maneuver.
It's brilliant. And maybe a very personal question there. On your slide one, Sense Plan Act and neural networks, is the Sense Plan Act hardware, hardware agnostic, or is there any limitations from hardware, or like any constraints in general?
Of course, hardware, and I could do an entire presentation about that. It's one of the main things, because so far all the hardware has been made for conventional vehicles, and what we actually need is to bring on about a partner, which we do. So we will cooperate with NVIDIA and Qualcomm. That it's born for autonomy. So give the performance, give on about the particular central architecture and cloud connectivity that is needed in order to pull those petabytes of information that are needed on real time. So that is the main thing. So it's got to be then a hardware made for autonomous driving, instead of what the current limitations that we have by using level 2+ hardware. So that is one of the things we got to completely redesign our hardware for autonomous driving.
Brilliant. Thank you very much, Catherine, for your time.
Yeah.
Very, very insightful.
And thank you for the time of all people listening today, and have a good